Okay, we're going to talk about what you need to know about calculus to do a calculus-based physics course, to begin a calculus-based physics course. These are things that should be very clear from a first-year calculus course, which of course is prerequisite to a calculus-based physics course. Sometimes they can be taught as co-requisites, in which case I would still talk about these ideas, but in a slightly different way, since I couldn't then assume that people already knew some calculus. Now, in studying calculus, you often lose the forest for the trees. You learn to do all the calculations, but you lose track of what they mean. And in my own experience, as an undergraduate, I really never understood a course really well until I used it in the next course in the sequence or in some other course. Most people are probably in that position. Some people, of course, never really understand it due to limitations of aptitude or study habits or time or whatever it might be. But that, the thing I described as a fairly typical sequence of events. We don't have mastery until we've used the course, and we haven't used the content of the course until sometime after the end of the course. So we're going to use the content of your calculus course in this physics course. We're going to use a little bit of the content. There are many things you do in a calculus course that aren't necessary for a first calculus-based physics course. What you actually need is fairly rudimentary, but you have to have developed a certain sophistication in your thinking about calculus to apply it effectively. Okay, well, enough of that. Here's two things you need to know. This is the fundamental of calculus. If y is a function of x, then y prime of x, which we can also denote dy dx, is what? It's defined as the limiting value of delta y over delta x, delta y being a finite change in x, delta y being a finite change in y, delta x being a finite change in x at some value x. And this is therefore the rate of change at x of y with respect to x. Okay, because this is change in y over change in x. This is an average rate of change of y with respect to x. And if you don't know what we mean by an average rate of change of y with respect to x, and you've been through a calculus course, you're missing the first fundamental bit of understanding that you need in the very first few weeks of the course. Doesn't mean that everybody understands this, as I repeatedly experienced. People come out of calculus course not even being able to tell me what a rate of change is. And it's the fundamental concept. So again, it's really important to learn that, and there are videos elsewhere that address this. I'm not going to address it here. You should understand that this is a rate of change of y with respect to x, and that when we take a limiting value, shrinking delta x down and delta y shrinking down accordingly, this ratio approaches some constant value, and that's the rate of change of y with respect to x at x. Okay? And that can be illustrated by a picture, but we'll get into the picture. The other side of the coin. Let's say that y of x is the rate of change of some other quantity q of x with respect to x. So we could write y of x equals dq dx if we wanted to, but I just want to talk in terms of the concept and the words rate of change, because that's what people lose track of. Not everybody loses track, of course, but most calculus students, I'm afraid, do. Okay, so if y of x is the rate of change of q of x with respect to x, then the integral from a to b of y of x dx is equal to the change in q of x corresponding to the interval a less than or equal to x less than or equal to b. Okay? Now, there's a reason for that, and I'm illustrating that reason with a couple of diagrams here. Before we go any further, I'll just say that the derivatives and integrals that you actually have to do in a first-year physics course are really very basic, very simple integrals. You have to know the chain rule for some applications, for many applications. You don't have to do a whole lot of even integration by parts, although some integration by substitution always crops up, and a little bit of integration by parts in certain cases. So you're not using the most difficult advanced techniques. You're not going to do a lot of partial fractions in a first-year physics course, but of course you should know first-year calculus well enough that if that does arise, you can review it and utilize it. Trigonometric substitutions, not that much, not in first-year physics. Okay, now let's talk about why this is rate of change of y with respect to x, and why this gives you the change in the quantity q of x. Okay, here we have a graph. We have 2 points, which I'll call x and x plus delta x. That's got to be familiar to you. This is almost universally taught. You might not quite see it in a diagram like this, but we're just saying that right here is the graph point corresponding to x. Here's the graph point corresponding to x plus delta x. And this segment here has length that's equal to the y value, y of x. This segment has length equal to the value of y at x plus delta x. So that's all very consistent, and you should completely understand that. Now, what do we mean by the slope of this line segment here? Slope of this line segment, first of all, I want to use a contrasting color here. That doesn't contrast enough with the yellow. Okay, first of all, I project across here, and it's very straightforward that from here to here is the same as from here to here. Implicitly, these are vertical lines, so they're parallel. The distance from here to here is delta x, so that this distance from here to here is delta x. Now, from here to here, what's the distance? Well, from here to here, you're going from y of x up to y of x plus delta x, so that this distance here, and let's say displacement, okay, we go from here to here, our displacement is positive delta x. Okay, from here to here, our displacement is y of x plus delta x minus y of x. And when I say displacement, I mean distance with a direction. Okay, distance is always positive, but this can be positive or negative. Okay, we could actually let this be positive or negative. If we came back this way, it'd be negative delta x, and then we'd have to come down this way with our rise. In any case, our slope equals y of x plus delta x minus y of x divided by delta x. That equals change in y divided by change in x. And I could write that as delta y over delta x. And that equals what? Well, that equals the average rate of change of y with respect to x. I'm going to go off camera and write that down because we're using up some time here. Okay, I extended this green segment all the way up to the yellow line. Okay, well, if I replace this trapezoidal figure with this one, we see that the slope at this point is much closer to the actual trend of the graph than it was here. Now, the slope here is the average slope of the graph between here and here, and it represents the average rate of change of y with respect to x. But our average slope here is much closer to the actual slope at this point. And as we shrink this down in the limit, we get closer and closer to the actual slope and ultimately approach a slope that represents the slope of a tangent line. So I'm going to write a statement. Okay, as I often do, I didn't leave myself a whole lot of room here, but hopefully I wrote that clearly enough that it's easy enough to read. If delta x is smaller, we get a better representation of the graph behavior at the point x, y of x. So as we allow delta x to shrink, we get much closer to the behavior of the graph at this point, and we approach the slope of the tangent line, which is the instantaneous rate of change. Now, we don't need a picture, we don't need a tangent line to define the instantaneous rate of change. We just define it as the limiting value of this difference quotient here with no reference to a graph, and we have a perfectly good definition. But we can use the picture to give us a better representation of the situation, and that representation is very valuable. Also, this is the value of y prime of x for this particular x, and of course we can do that for every x. So we have a derivative function, and we know how to take simple derivatives. Okay, that's what it means. You probably noticed I did a really quick change, and you probably noticed that as I approach the board, I don't have the highly reflective light blue shirt washing out what you see on the board, and I noticed that happening, and I hadn't thought to do that before. I keep a non-reflective, less reflective shirt handy in case I do wear something that reflects a lot. Okay, well, anyhow, let's look at this one now. If y of x is the rate of change of q of x with respect to x, then the integral from a to b y of x dx equal to change, etc. Let's see what that means. Okay, well, we have a similar picture, but I'm going to call these points A and B. We have y of A and y of B. And then in the middle here, you see I have a segment that I've labeled y of A plus y of B over 2. This being a straight line, this is supposed to be the middle, and it's clear then that this distance will be the average of these two. And what does that represent? Okay, well, remember that y of x represents the rate of change of q with respect to x. So y of a plus y of b over 2 is the average of these two rates of change. And that's approximately equal to the average rate of change on this interval if the function doesn't vary too much from this straight line. And if you make the interval small enough, it won't. Okay, well, when we multiply the average rate of change by the width of the interval, what do we get? Well, if we multiply this average rate of change by delta x here, then we're multiplying the average rate of change of q with respect to x by change in x. That's going to give us a change in q, corresponding to the delta x between A and B. So we're getting the change in q, and of course, well, and let's see what that represents. On this picture, if I make a cut here, I get this triangle up here. Okay, let's take this triangle, cut it out, turn it over, and paste it here. Okay, now what do I have? I have a rectangle whose altitude is y of a plus y of b over 2, and whose width is our delta x. In other words, the altitude or the length of this rectangle represents the average rate of change of q with respect to x. Delta x is, of course, the change in x, so that the area of this rectangle represents this quantity. So the area of this rectangle, which is identical to the area of the trapezoid, since we just took this off the trapezoid and pasted it here to get the rectangle, also represents the change in q. The area is y of a plus y of b over 2 times delta x, which is the average rate of change times delta x, representing the change in q. Now, more generally, your y of x function could represent a function that goes all over the place on an interval from a to b. We can't expect a straight line from here to here to give us a good representation of the behavior of this function. But if we partition the interval into a bunch of smaller intervals and approximate on each interval, we do get a good approximation.